Welcome to This Explainer. Today, we're diving straight into the anatomy of a really critical electric vehicle failsafe. We're going to tackle the high-stakes threat of total voltage sensing failures in battery management systems. Basically, we're unpacking the exact technical specs and functional safety strategies that engineers use to prevent the dreaded P0BFA and P0A8E diagnostic trouble codes. For those of you who know, those codes point to a severe total voltage sensor circuit anomaly. And look, when a battery pack's energy monitoring fails, the risk of high voltage arcing or just completely losing power on the highway becomes very real. So we're going to break down how engineers solve this massive problem across 5 distinct dimensions. Let's get into it. Here is how we're going to break this down today. First, we'll look at the root causes, the threat. Second, architecture, the brain. Third, DFMEA, design, the shield. Fourth, the PFMEA, process, the forge. And finally, validation, the proving ground. Okay, Section 1. Root causes, the invisible threats to battery voltage sensing. To build a fortress, we first have to understand the enemy, right? In a battery management system, the independent total voltage sensor isn't just there to show you the battery level on your dash. It's an absolutely vital safety benchmark used for high-frequency dynamic cross-checking. But the threats to it are actually these invisible physical, chemical, and material failures hidden deep within the components themselves. We're talking about 4 main culprits here. First up is thermal drift. You've got these mega-ohm precision metal film resistors measuring up to 1,000 volts, sitting dangerously close to heat-generating modules. Over time, that intense heat actually causes metal atoms to migrate and oxidize, which permanently shifts their resistance and distorts the voltage reading. Second, if the battery box loses its airtight seal, even a tiny bit of moisture ingress creates parallel resistance pathways, dragging the measured voltage abnormally low. Third, we have optocoupler aging. The high-voltage isolation circuits suffer nonlinear aging under that high heat, meaning they literally lose their signal conversion efficiency. And finally, connector fretting. Basically, constant road vibration causes micro-wear on connector pins, oxidizing them and instantly spiking the contact resistance. So with these physical threats just constantly looming in the background, it makes you wonder, how does the system's brain actually catch a failing sensor before it leads to a catastrophic event like high-voltage arcing? Think about it. If a resistor's value slowly drifts because of heat, or a pin slightly oxidizes, that shift is totally invisible to the naked eye. Yet the vehicle must somehow realize in real time that it's being lied to by its own sensors. Section 2. Architecture and Diagnostics. The system's brain. This brings us to the ASILD functional safety architecture. This is the incredibly fast, highly redundant brain of the battery pack. To trust the voltage readings, it uses this brilliant concept called asymmetric redundancy. It's kind of like having 2 independent auditors calculating the value of the exact same bank vault, but using completely different methods so they don't fall for the same illusion. On one side, the main board directly reads the total pack voltage through isolated hardware, but on the other side, the MCU software is continually adding up the voltage of every single individual cell to get a total sum. And here's the kicker. These 2 pathways use completely independent 5-volt reference power sources and separate physical routing. Why? To prevent common cause failures, so a single power supply drift won't take down both systems simultaneously. The brain just sits there cross-checking these 2 totals every 10 to 20 milliseconds. Now, if biodynamic cross-check spots a difference of, say, over 10 to 15 volts, boom, the system instantly triggers voltage failsafe mode. Instead of just immediately cutting the main contactors, which, by the way, could cause dangerous high-voltage arcing under load and completely strand the driver at highway speeds, it handles it much smarter. The system discards the corrupted total voltage data, falls back purely on that sum of the individual cells we just talked about, limits charging and discharging power to 50%, lights up the warnings, and lets the driver pull over smoothly and safely. But there is a major mathematical hurdle here. When you floor the accelerator, you send a massive surge of current through the system. That massive current hits the physical resistance of the copper bus bars and relays, creating a huge temporary transient voltage drop. The main pack sensor sees this drop, but the individual cell sensors don't. So, if the software didn't mathematically estimate and detect this bus bar impedance in real time, the system would think the sensors were failing and just falsely trigger shutdown every time you tried to accelerate. Section 3. DFMEA Design. Building the proactive shield. Let's look at how engineers build a proactive shield during the design failure mode and effects analysis, or DFMEA phase. This is where they plan for the absolute worst-case scenarios. Because a sensing failure could paralyze the vehicle's pre-charge checks and literally lead to a battery fire, it carries an extreme severity 8 rating. If the car turns on and can't accurately read voltage, it might allow a massive current surge that welds the main relay shut. So yeah, engineers absolutely cannot cut corners here. This proactive shield essentially relies on 4 major design steps. Step 1. They physically block extreme currents by placing high-voltage microfuses and limiting resistors right at the input. Step 2. They strictly adhere to safety standards for creepage and clearance. That means making sure the physical distance between high-voltage traces and low-voltage grounds on the circuit board is wide enough to prevent any micro-discharges. Step 3. They mandate the use of ultra-stable precision resistors that drift less than 15 parts per million per degree Celsius. And Step 4, which is actually my favorite, while the car is just sitting there sleeping in your garage, the system actively injects a test reference voltage into the circuit to verify that the amplifiers and converters haven't drifted. It diagnoses itself before you even turn the key. Section 4, PFMEA process, the manufacturing forge. But obviously, a perfect design is completely useless if it's built poorly, right? That leads us to the intense manufacturing process controls known as PFMEA. On the factory floor, absolute scrutiny is applied to neutralize those initial threats we talked about. Look at this table. To stop thermal drift from cracking solder joints, they use 3D automated optical inspection to measure the exact volume of solder paste. To stop moisture ingress, every single battery box goes through a 100% helium leak test to guarantee an IP68 waterproof rating. They seal the circuit boards in a high-density vacuum-conformal coating to eliminate any electrochemical migration paths. They even do metallographic crimp checks, literally taking microscopic cross-sections of the wire harness crimps to ensure they aren't squeezed so tight that they develop micro cracks. Section 5. DVP and R validation, the ultimate proving ground. Finally, before any of this hardware can hit the streets, it has to survive the brutal reality testing of the DVP and R validation phase. Remember that heavy acceleration problem we talked about? Well, to handle explosive acceleration without triggering false faults, the entire system's hardware sampling has to synchronize globally, and I mean globally, across all sensors within an incredibly tight 1 microsecond window. When testers slam the battery with dynamic currents of over 100 amps per millisecond, the main controller sends a broadcast latch command. Every single cell sensor and the main total voltage sensor must take their reading at that exact same microsecond. If they're out of sync by even a little bit, the rapidly changing voltage causes a mismatch and the car falsely triggers a safety shutdown. Engineers will also literally force the system to adapt in real time. During a hardware-in-the-loop test, they will intentionally and secretly inject a tiny 5 milliohm resistance to mimic a loose oxidizing busbar bolt. As massive currents flow, that 5 milliohm resistance creates a significant voltage drop. The software has to detect this brand new parasitic resistance, update its internal impedance model, and mathematically reverse compensate for it in under 10 seconds. And it has to do all this with an accuracy deviation of less than 5%, keeping the voltage readings within a healthy 1-volt margin so no false alarms go off. It's incredibly demanding. And to wrap up the manufacturing side, every single battery pack undergoes a rigid end-of-line dynamic calibration. Automated testers inject highly precise direct currents ranging from 100 to 800 volts into the system to dynamically calibrate the sensors. They are dialing in the out-of-the-factory accuracy to within plus or minus 0.1%. As this quote highlights, the static absolute pressure difference tolerance is controlled within half a volt. Those calibration checksums are then locked into memory and uploaded directly to the manufacturing execution system database, absolutely ensuring that 0 assembly errors ever leave the factory. Which leaves us with a really fascinating final thought for a future explainer. We've seen how this 5-dimension failsafe protects the battery today, from physical fuses all the way up to dynamic software compensation. But as these vehicles age, as those total voltage sensors inevitably start to drift 10 or 15 years down the road, how far can we push software algorithms to actively heal physical hardware failures in real time? Will dynamic algorithm models become so advanced that they can essentially rewrite the physical laws of the aging system to keep us driving safely? It is a thrilling frontier in EV engineering. Thanks for diving into the anatomy of this EV failsafe with me. Keep wondering and keep learning.